Hello everyone, Assalamualaikum warahmatullahi wabarakatuh and very good day. Welcome to my video. So basically this is a lecture video for course code EPO 460 Power Engineering, and in this video we are going to continue our lesson on the chapter electrical machines. Okay, so basically this is a part 3 of this video which we will going to cover on topics on type of DC machines. Okay, so my name is Dr. Nur Zulaili binti Muhammad. Here is my email address, so you can just feel free to email me whenever you have a question regarding the content of this video. Okay, all right. So this is a list of contents for chapter electrical machines, and in this video we are going to cover only for subchapter types of DC machines. Okay, right. So let's move to the subchapter of types of DC machines. Okay, so basically for the types of DC machines, it is classified according to the way in which their fields are excited. The fields or the stator winding can be either excited by separately excited or self-excited. Okay, all right. So let's go to the first type of DC machine, which is separately excited winding. Okay, so for the separately excited winding, we need to use the external source in order to create the magnetic field. So that's why we said it as a separately excited. So for this type of machine, there is no direct connection between the field and armature circuit. Or in the other words, there is no direct connection between the rotor circuit and stator circuit. For example, let's have a look at the equivalent circuit of the separately excited DC motor. Okay, as you can see here, this is the stator circuit and this is the rotor circuit. Okay, so there is no direct connection between stator and rotor. Okay, for the stator winding, or we can also call it as a field winding, we connect it to the external DC supply in order to create the magnetic field at the stator pipe. Okay, and then at the rotor pipe, we also have different DC supply. Okay, so this DC supply is used in order to generate the electricity in order to move the motor. Okay, all right. So for the separately excited DC generator, okay, so there is also no direct connection between stator and rotor. Okay, the difference between motor and generator is just that the flow of the direction of the current. Okay, for motor, the current will flow from the supply to the motor. Okay, but for the generator, since for generator we generate the electricity, so the current will flow towards the load. Okay, so usually we will connect load at here. Okay, all right. So next, let's have a look at the example 4.2. Okay, the question here, if the no load voltage of the separately excited generator is given by 135 volt at 850 RPM, what will be the voltage if the speed is increased to 1000 RPM? Assume constant field excitation. Okay, so the solution for this question is, first of all, we need to use the formula of for the EMF generated. Okay, so the formula is given by Z, the conductor, multiply with the number of pole, multiply with the number of flux, multiply with the speed, divide by 60. C is represented by the current path. Okay, consider the constant K is equal to Z multiplied with P divided by 60C. So therefore, this equation can be further simplified to become EMF equal to K multiplied with flux multiplied with N. Okay, since you have two different conditions, the first condition, the speed is equal to 850 RPM. And the second condition, the speed is equal to 1000 RPM. So that's why we will write the equation into two different equations. E1 represent the EMF generated for condition number 1, and E2 represent the EMF generated for condition number 2. Okay, and then the question also state that since it has a constant field excitation, so meaning that we can consider if the field excitation remain the same, so the flux also same between these two conditions. Okay, so flux 1 is equal to flux 2. Okay, so let's say we consider, let's say we divide equation first and the equation number 1 and equation number 2. So it become E2 divided by E1. It will be equal to K flux 2 and 2 divided by K flux 1 and 1. Okay, so K over K we can cancel out. Flux 2 is equal to flux 1, so we can cancel out. So now the equation become N2 divided by N1. Okay, alright, and then after that we can just simply rearrange the equation. So E2 now is become E1 multiplied with N2 divided by N1. Okay, and then we just substitute all the number accordingly. And then the final answer will be the EMF generated for the speed of 1000 RPM will be equal to 158.8 volt. Okay, alright, so that's the solution for the example. Okay. Then next, we go to the second type of DC machine, which is self-excited winding. Okay, for this type of machine, there is a direct connection between the armature and field circuit, meaning that between the rotor and stator, there is a direct connection. Okay, so the armature winding will provide the current to create the magnetic field. Okay, meaning that your rotor part will actually provide the current to the stator part in order to create the magnetic field. It may be classified as a 3 different types. Okay, the first one is the series excitation. So for the series excitation, the field winding and the armature winding is connected in series. Okay, for the second one, which is shunt excitation, it means that your field winding and the armature winding is connected in parallel. Okay, the third one, which is compound excitation, it means that your field winding is connected to the armature winding by series and parallel. It is actually a combination of series and parallel connection. Okay, all right. So first we go for the first type, which is series excitation. Okay, so here you can see that RA is the armature winding, RF is the field winding. Okay, so there is a direct connection between armature and also field. Okay, so meaning the armature represent rotor, field represent stator. Okay, so you can see there is a direct connection. So the connection is in series type. Okay, so that's why we call it as a series excitation. Okay, for generator, since we generate the electricity, so the current will flow towards the load. Okay, so here is the equivalent circuit for the series DC motor. Okay, so the only difference between these two is the flow of the current. So here for motor, since motor we need electricity, so that's why we need to put supply here. So the supply, the current will flow from the supply towards the motor. Okay, so when we try to apply the KVL across this loop, you can have that EG will be equal to V terminal plus IA multiplied with RA plus RF. Okay, since it is in series, so that's why here you have RA plus RF. For the motor, if you apply the KVL across the loop, the equation will be EA will be equal to VT minus IA multiplied with RA plus RF. Okay, all right. So next, let's have a look at the shunt excitation type. Okay, for shunt, it means that your armature winding and also field winding is connected in shunt. Okay, you see RA and RF is in shunt connection. Okay, all right. For generator, since generator generate the electricity, so that's why here the current, armature current coming towards the load. Okay, and then for motor, since motor need electricity, so that's why we have supply here, and the current will coming over the supply go to the motor. Okay, all right. So for example, if we apply the KVL across this loop from this point to here and then until here, we can get the equation is equal to EG is equal to VT plus IA multiplied with RE. Okay, so here voltage drop across the RE. IA multiplied with RE. Okay, so in the equation there is no RF since RF is located at here. RA is here, so the KVL we do across this loop only. Okay, so that's why your equation only have EG will be equal to VT plus IARE. Okay, next for the shunt DC motor, the equation will be EA equal to VT minus IARE. For generator, we have plus, but for motor, we have minus. Okay, all right. So the third type, which is compound excitation. Okay, for the compound excitation, the armature winding is actually connected to the field winding by series connection and also shunt connection. Okay, so it's a combination of series and shunt. So here you have RA, armature resistance, and you also have field resistance, but the field resistance have two different types. The first one is at series location, the other one at the shunt location. Okay. Okay, so for generator, since generator generate electricity, so that's why IA is out, coming out from the generator, go to the load. Okay, for motor, since motor need electricity, so that's why we put supply here, and then current will flow from the supply to the motor. Okay, so IA is coming towards the motor. Okay, for the equation for the compound DC generator, we apply KVL from this point up to this point. Okay, so if we apply the KVL, EG will be equal to VT plus IA multiplied with RA plus RF2. Okay, RA plus RF2. Bear in mind the equation wouldn't have RF1. Okay, because RF1 is located at the shunt location. Which for the equation, we only consider on the resistor that connected in series, RA plus RF2. Okay, but for the compound DC motor, the equation will be EA equal to VT minus IA multiplied with RA plus RF2. Okay. Next, for further understanding, let's have a look at the example 4.4. Okay, for this question, we will see on the example on how to solve the problem related to the series motor. Okay, so the question here, find the counter EMF for a series motor running at 1500 RPM at 51 ampere with a 120 volt source, 0.12 ohm field winding, and 0.1 ohm armature resistance. So for the solution, maybe we can start by drawing the circuit first. So here the circuit for the DC series motor. Okay, and then the speed is given by 1500 RPM. IL is given by 51 ampere. So IL is actually current flow from the supply. V terminal is equal to 120 volts. So V terminal is here. RF is given by 0.12 ohm. RA is given by 0.1 ohm. So here 0.1 ohm, here is 0.12 ohm. Okay, so first armature current. Okay, the question asking about the what is the value of the counter EMF. So we need to determine the value of counter EMF. So first of all, we need to define what is the armature current. So here, since it is series circuit, so armature current IA is equal to IL equal to 51 ampere. And then we can apply the KVL across this loop. So EA will be equal to VT minus IA multiplied with RA plus RF. Okay, and then we just substitute all the value accordingly. 120 minus 51 multiplied with 0.1 plus 0.12. And then the final answer will be the counter EMF is equal to 1008.78 volt. Okay, alright, so this is the example for DC series motor. Okay, next, for example 4.5, let's have a look if we want to solve the example for shunt motor. Okay, so basically the value for the components for the other component is just the same, but we just change from series become shunt. Okay, so in this question, it asks us to find the armature current, what is the IA and what is the counter EMF. If the circuit is in shunt motor, the speed is the same. IL is also 51 ampere. V terminal also same, 120 volt. But now RF is equal to 120 ohm. For example 4.4, RF is 0.12 ohm, right? But here, since it is shunt, so RF is equal to 120 ohm. RA remain the same, 0.1 ohm. Okay, alright. So in this question, for the solution, maybe you can start by drawing the circuit first. Okay, so here you have a DC shunt motor. Okay, so the question asks you to find what is the value of IA and what is the value of EA. Okay, so so first of all, we need to determine the value of IA. Okay, so by applying the KCL, the Kirchhoff current law here, you know that the current go into IL will be equal to IF plus IA. Okay, so we can rearrange the equation become IA is equal to IL minus IF. Okay, IL is given by 51 ampere. And then IF you can calculate because IF is here. So by applying the Ohm's law, you know the voltage VT here is same as per voltage across the RF. So in order to find the IF is equal to VT divided by RF. Okay, so VT divided by RF. 120 divided by 120, you get 1 ampere. So now IF is equal to 1 ampere. So 51 ampere minus 1 ampere is equal to 50 ampere. So now your IA here is 50 ampere. Okay, and then we can apply the KVL across the loop. So from this point up to here and here, you get EA is equal to VT minus, EA equal to VT minus IARA. Okay, VT minus IARA. And then after that, you can just substitute all the value accordingly. Finally, you get your counter EMF is equal to 115 volt. Okay, all right. So that's how you calculate for the shunt. Okay. Okay, so now for example 4.6, let's have a look on the calculation for circuit DC compound motor. Okay, so here you need to find the armature current and the counter EMF for the compound motor running at speed 1500 RPM. The IL is still 51 ampere and the V terminal also is equal to 120 volt. But now you have three different resistors. The first RF, which is the series field, is 0.12 ohm. The shunt field winding is 120 ohm and the armature resistance is given by 0.1 ohm. Okay, alright. So the solution for this example, maybe we can start with drawing the circuit first. Okay, so this is the DC compound motor. Okay, so the speed is given by 1500 RPM, IL is equal to 51 ampere, VT is equal to 120 volt, RA here is 0.1 ohm, RF1 here is 120 ohm, and RF2 here is 0.12 ohm. Okay, so the question asks about the armature current and also the counter EMF. Okay, so now in order to calculate the IA, same as per shunt circuit, you need to apply the KCL here, the Kirchhoff current law here. Okay, so from the Kirchhoff current law, you know that the IA is equal to IL minus IF. So IL is given 51 ampere, IF is equal to V terminal divided by RF1. So here 120 volt divided by 120 ohm, so you get 1 ampere. So 51 minus 1, you get 50 ampere. So it is just same as per shunt circuit. Okay, and then after that, you need to apply the KVL to get this equation. Okay, so in order to calculate the EA is equal to V terminal minus IA multiplied with RA plus RF2. Okay, so make sure you put RA plus RF2, not RF1. Okay, because RF1 is located at the shunt location, but here RA and RF2 is connected in series. So that's why in the equation you put RA plus RF2. Okay, remember it is not RF1. So, and then after that, you can just substitute all the value accordingly. 120 minus 50 multiplied with 0.1 plus 0.12. So, finally, you get the value is equal to 109 volt. Okay? Alright. So, that's how you solve for different circuit for series, shunt, and also compound. I think that's all for now. Thank you for your time. Thank you for watching my video. In the next video, we are going to see on the concept on the power flow and also torque. Okay? All right. Bye.